Alright, hello. In this video we're looking at a new topic, antiderivatives. So just as kind of a setup, something to think about, we can imagine if we're doing some work, certain situations, we might know how something is changing. Maybe we're getting some data, somehow we're observing it, collecting it, whatever it might be, but we somehow understand how a quantity is changing, but we want to know something about the quantity itself. So, in the context of examples that we've seen, we might be measuring a rate of change, and we wanted to know the position at a certain time, and a function that would describe the position. In calculus terms, what this means is we want to find a function whose derivative is the function that we know. So instead of starting with a function and then figuring out the derivative, figuring out its rate of change, we're kind of going in the other direction, going kind of a reverse process. If such a function exists, it's called an antiderivative, and that's the name. Maybe a better name. Wait, see if I can write a little better. Reverse derivative. I don't know. I'm spending too much time just writing it, but it's a lot of things. An antiderivative, I mean, you might take it literally as just not derivative, and there's a lot of things that would be that. So it's a very specific idea. It's a function where we figured out by kind of reversing the procedure. So reverse derivative might make more sense, but this is the term that we use, is the term what we use in every calculus class you could ever take. So we're stuck with it. A little bit more formally, we have the following definition: a function f, and for now, early getting started, we'll use capital letters for our antiderivatives, corresponding to our original function in the lowercase. But a function capital F is an antiderivative of f on an interval I if f prime of x equals f of x for all x in I, capital F prime. So if the derivative of f prime equals f. A little bit more formal here, we're thinking about over an interval. Most of what we do, the interval certainly will be obvious, but most of the time it's the entire real number line. But not always. One thing that I want to note here is this word was not an accident. So we'll note we didn't say the antiderivative of a function, we said an antiderivative. And in fact, if a function has an antiderivative, then it has infinitely many, which at first might seem kind of weird, kind of crazy, but we'll think about it in just a second here. But for two quick examples here, f1 of x equals 3x squared, f2 of x equals 3x squared minus 2. These are both antiderivatives of this function. Lowercase f of x is 6x. We verify that by just taking the derivative. The derivative of capital F1 is 3 times 2, so 6x. Bingo. Here we get that 6x minus 0 would be, so that's just 6x, same thing. And the relationship that you see here is true in general. So although there might be infinitely many antiderivatives of a function they're all similar in the following sense. Any two only differ by a constant. So in this example, the part where we had things varying, had things changing, that part was the same, the 3x squared. The only thing that was different was that minus 2. And if you think about that geometrically, what you've got is, if you got an antiderivative or if you got a function, you add a constant to it, it just amounts to a vertical shift, right? And so that rate of change isn't affected by that. If you had, if I had a function that looked like this, and then I took the same thing and shifted it up as best I could by however many units, when I'm looking at maybe the tangent line here, it's the same slope, right? So that's the idea. So the plus 5, the minus 2, the plus 3, whatever it might be, that differing by a constant doesn't affect the derivative because it's the derivative of that is 0, so it doesn't affect the rate of change. So it turns out that antiderivatives are unique up to that constant. And as you mentioned, we saw that earlier. So when we're talking about the collection of antiderivatives for a given function, it's commonplace, and we'll start doing this so often that we won't, we'll just do it second nature. But we use this generic. It is a little bit weird at first, but we use this generic placeholder that we just call, almost always we call C. Sometimes if we're working with something specific, maybe a cost function that we called C, we might use capital K or something. But usually we would just use C. It's kind of, like I said, a generic placeholder for a constant. So if f is an antiderivative of f, we say f of x plus c is the most general antiderivative. The most, maybe we would have in parentheses, but we'll leave it there. And c is an arbitrary constant, or like I said, I feel like kind of a generic placeholder for a constant. So in some sense, really, that's a collection, that's a set of functions, but all the important information is in the capital F of x part. And even if there's a constant there, you can, it's not the part to worry about. If we're doing something and somehow we say the antiderivative of a function, again, there's not a single one, but what we would typically mean, if we don't have any other additional information, we would mean the most general antiderivative, or the general antiderivative. On the other hand, if we have some additional information about the function, maybe we know that at 1 the function equals 16, then we can narrow it down. Instead of having all these possible antiderivatives differing by a constant, we can figure out which one it is exactly. And if you jump back to the little sketch I had here, if I looked at all these possible antiderivatives, that would be shifts up of this curve here. If I knew that at 0 it had to pass through whatever this value is, then I would have a unique one that goes to that point. And then I have the antiderivative that's the solution of, or it satisfies what we often call an initial condition. So we've got general or most general antiderivatives, and then we can find particular antiderivatives if we have this extra bit of information there. So for example, most general antiderivative of f of x equals 6x is this, and we are a little sloppy here because here we've got a function. Here it's kind of a family of functions, so it's a set of functions. That said, we usually kind of just think of one particular example. It's just, we're kind of sloppy with it, I guess. But if we're told in addition that f of 1 is 2, then you have a specific, you have a particular, the one antiderivative that satisfies that, and that is this guy. So that would be c is -1. So it's the specific one whose derivative is 6x, and f of 1 is 2. So now for finding antiderivatives, we're going to spend a lot of time down the road, and even in the follow-up courses, thinking about and learning about how we might do that. But again, we want to keep in mind that it's kind of this reverse process to differentiation. So for now, what we're doing is taking the basic differentiation rules and just looking at them, like we said, in reverse. So very basic tools for us getting started. For example, this would be the power rule. If f of x was x to the n for n not -1, then a particular antiderivative is capital F of x is x to the n plus 1 over n plus 1. Quick check. Derivative of capital F here would be, well, the n plus 1 comes down times x to the n plus 1 minus 1, so just x to the n, all over n plus 1. So that's right. Right, so again, just kind of working backwards from the power rule. That was a basic rule we had. For this one, it would be a trig rule, and we can check. So if our function was sine of x, an antiderivative of would be negative cosine of x. Capital G prime is negative so derivative of cosine of x is negative sine, right? And so negative of that negative times negative is positive. So sine of x is that derivative, and that's what we had there, so that checks out. And there are plenty more. I didn't list all of them here, but for additional rules, at least again for us at this point, we can write out derivative rules we know, reverse this process. For example, this would just be another case like the two we looked at. We know one of our differentiation rules. This is just kind of explaining the process for how we came up with something like this or this. Since the derivative of b to the x is natural log of b times b to the x, usual, b is positive, b is not 1. Then the function, this function has capital F of x being 1 over natural log of b times b to the x as a particular antiderivative. So think about it this way, when we differentiate, we multiply by that factor. So if we're going to reverse the process, to figure out an antiderivative, we would divide by it. And like I said, we'll learn more tools to be able to come up with these more of these formulas down the road. But for now, we're just basically taking that list of the very basic differentiation rules and kind of flipping the direction, so working backwards. All right, so that's all we got for you at this point. So antiderivatives, again, maybe think of it as a reverse derivative, or antidifferentiation as a process, reverse differentiation. But the idea is you want to find a function whose derivative is the function you're given. So you're kind of working backwards. We'll be spending a lot of time with this moving forward, so we're just getting our feet wet, just getting started at this point.